And probability is kind of a weird thing. We're going to be with it for a while until probably the start of the next semester. It's not everybody's favorite thing. Amazingly, though, there are those of us who just have a natural ability with probability, and it just seems so intuitive and easy, and then the rest of us are like, ugh, probability. Well, a couple of things. First of all, it's worth it to learn it. I mean, we're learning about situations that are just due to chance. Remember that expression? We used it a whole lot even last chapter. And it's going to continue on into inference, so it's a good bridge. And even if you just did probability for probability's sake, it's a pretty lucrative field. If you can help a company predict outcomes based on what the chance of them happening, you could go into insurance, you can work for large companies, you can look at probability as it relates to climate change. I mean, there's all kinds of jobs available. But people don't like probability, so that means there's a lot of demand for those jobs. So don't just write it off. It's something good. And, that said, if nothing else, we're back to being into some kind of computational math. So here we go. This is going to be a really kind of a quick lesson, and it doesn't have too much to it. It's more sort of entry-level stuff. So here's some introductory terms. So probability is a branch of math that describes the pattern of chance outcomes. And probability outcomes are the basis for inference. So it is where we're headed, and it's a necessary building block toward that end. All right, too often when we talk about randomness, some people just imagine, a ball just bouncing around in a box and not really heading in any direction and not really all that predictable and just kind of haphazard. But that's not what we're talking about here. Randomness, as far as probability goes, is actually a certain kind of order that emerges in the long run when repeated events occur. So if you roll a die and it comes up 1 more often than not, you know that unless there's something weird with that numbered cube, that 1 should only happen 1 every 6 times. And if you're seeing it more than that and you've only rolled it like 20 times, you just didn't roll it long enough. If you roll it indefinitely, it should come up, any of the numbers should come up 1 out of every 6 rolls. But that's the kind of order that you would see in the long run. In the short run, anything could happen. All right. We call a phenomenon random if individual outcomes are uncertain. Remember, if I roll a die 4 times, it doesn't mean or 6 times, doesn't mean I'll get every single number once. All right. Individual outcomes are uncertain, but there is a regular distribution of outcomes in a large number of repetitions. All right. Too often, when you see the word large in statistic, it means immeasurably large, infinitely large, or infinite number of repetitions, that kind of thing. All right, so an experiment, this is any sort of activity whose outcome cannot be predicted with certainty. All right, and that's even back when we were doing experiments as far as an experimental study. We went into it with all of the best intentions and the best ways of handling things, and we just waited to see what would happen because we didn't know. Okay, so in this case, this is kind of simple experiments: flipping a coin, rolling a die, drawing a card, whatever. Okay, an outcome, that's one of the possible things that can occur as the result of an experiment. All right, sample space is the set of all possible outcomes. All right, so if I flip a coin 1 time, my sample space is that I can either get a head or a tail. That's it. 2 outcomes, 1 out of 2, 1 out of 2. I get 0.5 probability for each particular outcome. That's my entire sample space. Now you do write it with this formality. Capital S stands for sample space, equals, and you have to put your outcomes in braces like this. All right, when you flip 2 coins, you get a little bit more action going on, because you could get a head on the first, a head on the second, a head on the first, a tail on the second, tail on the first, a head on the second, and 2 tails could be another one. So you've got 4 outcomes. All right. If you flip 3 coins, there are going to be 8 outcomes. And it's exponential. See, 2 to the first, 2 to the second, 2 to the third. All right. And you can see you get every combination of outcomes from 3 heads to 3 tails, right? You have 3 ways of getting 2 heads. You have 3 ways of getting 2 tails. So if it was 4 coins, wouldn't there be 16 outcomes, 2 to the 4th? And if there were 5 coins, there'd be 32. The sample spaces get a little hard to list, but there are times where we do list a bunch of things in sample spaces. If you ever need it, and I don't know that too many people actually do this, you can build this in a tree diagram. So 3 flips of a coin. The first one could be a head or a tail, and off of that you can get a head or a tail, and off of those 4 things you can also get a head and a tail, and you just follow up branches, okay? So you could do head, 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 tail, head, tail, head, head, tail, tail, and just do the same thing down here. So, I mean, it's useful, but you don't see that too much unless you're asked for it. So some sample spaces can be written in words, and long sample spaces can be truncated. You'll see examples of those. All right, so other ways to count outcomes. You have this thing called fundamental counting principle, and it's super easy and it's pretty powerful. So this is a weird definition. If there are m different choices for decision 1 and n different choices for decision 2, then the first and the second decisions taken together can be taken m times n ways. And the best example, you ever get those menus jammed in your door or kind of rubber banded to the doorknob, to the, your outside door, from Thai restaurants or whatever, Chinese restaurants? Here is a menu. This is just a menu that's completely ridiculous because that's just too short, but just so that we can consume it easily. You have on a menu 5 appetizers, 10 entrees, 6 desserts, and 4 beverages. So how many possible dinners are there? A lot. So if you think about that menu that's being rubber banded to your doorknob, that thing is loaded, and you can come up with a huge number of possibilities just based on what's listed there. All right, combinations. Actually, fundamental counting can also be considered a combination. I'll get back to that. This is where groupings happen and you don't care about the order that you're looking at. And we're talking about n objects taken r at a time, like picking 2 greeting cards out of 10 possibilities. How many different ways can you do it? Well, here's how you work it. And if you've been in pre-cal, you've seen combinations used to do coefficients for Pascal's triangle values. So NCR, that means n things taken r at a time in a combination, or you can do like this, which is not a fraction. It's just n things taken r at a time, and it's factorial. N factorial divided by r factorial times n minus r factorial. And this is a very nice formula. In pre-cal, you may need to use it occasionally, We don't actually use it. We're going to rely on calculators. All right, so here are the instructions, but I'm just going to go ahead and show you. So for example, here's 5 letters. You want to take 2 at a time. All right, so it could be A, B, A, C, A, D, A, E, B, C, B, you know, just any 2 out of the 5. And it doesn't matter. A and B is the same as B and A. Okay? There are 10 possible combinations. If you list them all, here's the sample space. And that's all the possible combinations that are available. All right, so I'm just going to stop this, and we want to do 10 things taken 2 at a time. All right? And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let's see. I'm going to pull up the calculator, and I'm going to show you each kind. So for the few of you that have a 84 type calculator, you go under Math and Probability, and you can see NPR and NCR. We want NCR. The thing is, you've got to put your first number in before you even come here. So I'm going to quit out of here, if I can find it. And I'm just going to type 10, because I want 10 things taken 2 at a time. Actually, no, excuse me. Let's clear that out. That was 5 things taken 2 at a time. So here's your 5, Math, Probability, NCR, 2. And there it is. Just hit enter. You can do second enter, and you can change this number to 10 things taken 3 at a time. Also 10. You can do second enter and take 5 things taken 4 at a time. That's 5. Okay? So you can do 10 things. Well, actually, here, let's clear that out. You can copy this, and then you can actually go in and change the numbers. So 10 things. Oh, well. I guess if you're going to go to another digit, you got to find this again. So let's say 10 things taken 4 at a time. Ooh, there's a lot of ways. Okay? So if you want to do it on the Nspire, it's going to be different. Okay? So let's go ahead. We'll go into a calculator page, or not a calculator page, but just a scratch pad. And it'll be Menu and Probability and Combinations. And you don't have to put the first number in before all of this. All you got to do is put it in after the fact. So 5, 2. That's NCR, 5 things taken 2 at a time. And I'm a little concerned that my parentheses went away. So let's do this again. So Menu, Probability, and Combinations. And it's 5, 2. All right, 5 things taken 2 at a time. There's your 10. And you can come up here and copy and paste it, and you can change your numbers. So you can do 5 things taken 1 at a time if you want. Or you can just retype. All right, so there's combinations on both calculators. Now there's another thing here that you probably hadn't picked up in pre-cal people. And that's going to be permutations. So let's go here, current slide. All right, this is grouping where order matters, right? So in the previous problem, we had 5 things taken 2 at a time, the first 5 letters of the alphabet. And the thing is, A and B in combinations was considered the same as B and A, but not here. Permutations, A with B is different from B first then A. Okay, so you have one less thing that you're dividing by if you compare the formulas, so you should get a bigger number. So n factorial, I remember what n factorial is. Like if it's 5 factorial, it's 5 times 4 times 3 times 2 times 1. Okay, all right, so again, there's some instructions on the calculator, but I'm just going to show you. So here's the same thing, first 5 letters taken 2 at a time in any order. There are 20 permutations, right? So A and B and B and A are considered different because the order changes. And by the way, in order to figure out whether you have combinations or permutations, look for key words like ordered, arranged. If those words are there, that means it's permutations. If it's not there, then it's just combinations. So let's see what we've got here with the calculators. So starting out with this one, let's go ahead and do 5 things taken 2 at a time in permutations. So 5, back to probability. You already saw the NPR. And taken 2 at a time is 20. Simple. And it's going to be very similar for this menu, probability, permutations, 5, 2. So you don't have to put anything in first number-wise. Just go here and then put your numbers in afterward. And there it is. Okay, so combinations, permutations. All right, so we already saw this. Okay, be real careful because the number of permutations is not always twice the number of combinations. Just don't say, ooh, it went from 10 to 20, it must always do that. It just happened to do that. That's not always going to be the case. It does happen, but not always. Okay, worksheet. That's the worksheet that's combinations, permutations, and counting. And it's a fun worksheet. It's pretty cool. Now, what I wanted to mention while I'm thinking about it is I'm going to go all the way back to, if I can get back there. Come on. All right, be that way. If we go all the way back to the fundamental counting principle, all right. In this slide here, all we did was find all the different choices that were available that make up a dinner and just multiply them together. All right, couple of things. First of all, it's going to be an appetizer and an entree and a dessert and a beverage, okay? And in probability speak means multiply. So that's why you've got the multiplication. Actually, these are 5 things taken 1 at a time, which would just be 5. 6 things taken 1 at a time, which would be 6. 4 things taken 1 at a time. That would be 4. All right, so these actually are combinations. It's just that they're so simple that we're just going to use the numbers that we have and not write them out in that, combination language. If it's any more than 1 at a time, then you do have to write them out, 5 things taken 2 at a time, or 6 things taken 3 at a time, or 4 things taken 1 at a time, okay? But in this case, they're all taken 1 at a time. So just a little connection between combinations and counting. All right, so have at it.